Thank you for folks coming in person, to be able to online. The first thing I'm going to say is everything in this talk is extremely basic. It's just trying to cram everything I could teach about basic uses of machine learning for fMRI in 45 to 50 minutes. So if you're familiar with all of this, please feel free to run away. If you are listening to the talk and are here halfway through and decide that, yes, I didn't believe him when he said it was basic. It is basic. Please feel free to run away. I'm not going to be offended in the least. That goes for Ned and Fernando at the very least, and probably them, maybe other folks too. With that said, I'll continue. The other thing I wanted to say was feel free to interrupt me or ask questions at any point, because that's also the point of doing this in person, is that you can interrupt, and you can certainly send some questions at some other time if you want. Then, who is recording? He's recording. Okay, you have it. Okay, just wanted to check before I have on. Okay, so yes, I'll be closer to the owl and try to speak a little bit louder. But yeah, I don't think it's great, but I don't think I can put the owl anywhere other than where it is right now without it being kind of precarious for me going around cradling the owl with that. So I usually start the talk by going back to the definition, and people sometimes are surprised that people discussing machine learning and AI in the 50s, in fact, before. But generally, the definition that's in all textbooks is it's the study of computer programs that learn to predict or to do something and learn it from data and examples without being told how to do it explicitly. But even this definition has tons of caveats. The other things I've heard over the years, mostly with people trash talking each other, statistics and computer science department, would be, yes, it's like statistics in that it learns from data, but it's being implemented poorly from first principles, or it's like statistics, but it works in real-sized problems. Oh, sorry, it's fine. Thank you. I have enough faces here that I can see you cringe, which is the most important part. And stop saying the things. So, and these could be informal definitions that people bring up. Or you could think about it from the perspective of the way people typically think of it is they come to me and say, we want to learn to distinguish patients from controls. We want to predict some characteristics of the patient from the image. Or are there some groups of patients whose images are similar in some way? And often when people come to me, they come from one of these three angles. But the most important thing is it really depends. And the goal of the talk is to give you some idea of what depends on. And perhaps more important is science is about questions, it's not about methods. So often we tell people you don't need machine learning for this. What you need to do is use this particular statistical technique or this mathematical model or something else. So, and if you were to think about the questions that people ask as scientists, they generally fall in the four headings, i.e., they could be questions of description. So can the observations you have be explained with given variables? They could be questions of prediction. So is a certain outcome variable predictable from the observations that we have? It could be causality and control. So can we, if we are going to intervene in an experiment, what would happen? Be something about mechanism of computation. So what exactly is this neural circuit doing in transforming percepts into actions and so on? So most of machine learning questions, methods, or approaches are about prediction, but you could also make them fit on any of these questions, and that's why I say that it's. But rather than talk about this completely in a vacuum, and certainly for the members of the audience coming in now, I'll do the same warning of this is really basic. You probably know all of this already, so feel free to run away if you want to at any point. Because the last thing I want to do is about it. I think the best way to illustrate this is to talk about a technique that people would know from a statistics course, so linear regression, and see if you're taking a machine learning viewpoint of this technique, now you need to ask a prediction question. What's different from what you're used to doing? And the sequence of slides was a lot was Poldrack, who had a variant of this many years ago that I asked for permission to adapt. So think of a scenario where you have a question such as, is reaction time on a particular task related to age? As I can attest, over time, my reaction time slows for a number of tasks. It might be because of intrinsic failures, it might be because of increased wisdom, we don't know, but it's noticeable and can be measured. So if you wanted to answer this question and you had this sample, what you generally thought to do is align to it, i.e. you're fitting a model and you're reducing all the messiness of the observations to just a couple of parameters, namely, it's a line, it has a slope, it has an intercept. And that's a nice way of boiling down the messiness of a real-world sample to a description that says this is what we think is going on. And you can estimate these parameters using equations. We're taught how to do this. And so generally, asking this question is equivalent to testing the null that the slope is actually zero, and there's no relationship between one thing and the other. And in the null hypothesis framework, you would be asking how likely is the parameter estimate that you get by fitting the sample if the null hypothesis would be your p-value. You can crank this through central limit theorem, and in the end, you can produce a p-value out of it, which in this case is small because I generated the data and I can assure you that it does come from a line. And you get also an R squared, which is how much of the variance in reaction time is explained by which. Nothing wrong with this. And so what you can conclude from this is you would reject the null hypothesis that these two things are related. Note that you don't get a probability that the alternative is true, or people often think that that's the case. You get an R squared, which is a measure of how well this model fits the data. And you could get a confidence interval on that particular parameter, so just some uncertainty about how the model might vary, not too much. The test does not tell us how well we can predict RT from age in the population in general. Sometimes people think it as such. It doesn't tell us that this is the right model. We know it is the right model because I generated this line, but in reality, we never know. And it also does not tell you whether age, whether or how age causes reaction time. Of course, in order to do that, we know roughly in which direction the causation error goes, but it requires external knowledge. So when we talk about making prediction models, that doesn't mean that they are causal and the things you put in as inputs and the thing you have as output are causally connected. The causation people need a direction. So to go to prediction, I want you to think about what happens when you have a new sample. So if I were to go and from the same population do another sample, other people with other ages and other reaction times, how well would the model fit this? You can compute the R squared using the parameters from the original sample, and you'd find that the model that looked good in the original sample looks a bit worse now. It's not so surprising. It's a different sample after all. But if you start thinking, what's the real R squared? It's a somewhat disturbing question, because how much could you trust the R squared about? In fact, if you draw 100 million different samples and you compute on average how the R squared of the original model goes, it's always lower than what you got in the original sample. Again, you may be fitting some idiosyncrasies of that sample, but how do you know how much is just idiosyncrasies versus how much is real relationship? That's really what machine learning tries to answer. So it's we would like to get an estimate of how good the model would be on any new sample. So to deliver this point, you can be doing the same thing for two completely different reasons. You can be estimating model parameters so you can learn how to describe the messiness of the data. Or you could be doing it because you want to do prediction, different question. And you are just learning to model how the variables relate, so you can deploy it in your sample. And when you're evaluating, you can also do it for two different reasons. if you're thinking as a statistician and you want to describe how to say how good a description this is, you would be looking at goodness of fit, maybe penalized by how complex the model is. And if you're evaluating this for prediction, you want to apply the model to a test sample and see how well you actually do in a new sample from the same population. Does this make sense so far? Good point to run away if you think this is too basic. It is basic. So at this point, people say, yes, it'd be nice to do that, and maybe I would like to see how my model does in a new sample, but what if I can't get more sample? The answer is you always can get more, because since you can take your sample, you can split it in two, and now there's a training sample and a test sample from the sample you started with, and you can train a regression model on one half, and sample and test it on the other one. You can do the same, take it on average, and now you know how the model actually did. It's always possible to do this. In fact, the term for this kind of splitting of the data parts and training the model on the sum of the parts and testing it in the parts is called cross-validation, which you might have noticed. The term is generally to say you split it into k parts called faults, you train on all of them except one, test and then calculate the rate, and you calculate the average prediction performance of the full performance. So if you want to do it in this sample, and I'm just doing this for this because it's fairly small, I'm just leaving out one point. What does it look like as you just leave out one? I'm leaving out the one here in the corner. As I fit more lines and leave out different models, you end up with similar, slightly different lines. And you get an estimate. You can get an R-square from each one of them. And you can then average that and get this leave 1 point out estimate of the R-square. So it's conservative sometimes, but it's closer to the mean of 100 new samples than it is to what you're getting in the original sample. So it's an indication of how well you can do, maybe a bit conservative. And there are many considerations in doing this. So you assume that the models across the faults are pretty similar to each other. That's why this is kind of combine this into models. Typically, people do this in something like 10-fold cross-validation or V1 out, which is more expensive and has other issues. And it's a nice thing to do as long as you are sure that you are doing this for one model or for other model, for another model, and you always report results across all the experiments that you do. It's very easy for people to do cross-validation over many things and just pick one. If we have time at the end, I have a whole section on things that people do that are potential cause issues and inflate the results. And this is one of them. But what I would say is, if you are using cross-validation in any way, shape, or form, you should read the paper that's at the bottom. It's really good, covers pretty much every issue that there is, and you'll do better with it. So, and that would be it for how to do evaluation and why to do evaluation. Sorry, using the model for the purposes of doing prediction and evaluation. The other way in which this prediction perspective is useful is to answer the question of how complex is a model that fits the data that you have. So this image is of epicycles that were designed to fit known motions of the planets in a model that has the Earth as the center of the universe. You can make super complicated models for how the planets move that would allow this to be the case. So it's always possible. But the model might just be too complex. Because remember, I used a line in the previous example, and in the course, people will tell you fit a plane or fit a plane. Why? Why should reality be a line bar plane? But also, if it's much more complicated, how do you know you're not overfitting it? And thinking about this from a prediction angle also allows you to answer that question. If you're a statistician, you might say, my model fits well, but if it's too complex, it has penalized by something like the AIC or the BIC, you might say it still scores poorly because it's too complicated. And that's a statistical answer to this problem. Machine learning answer to this problem is to take a sample like this you can fit a variety of different models. So a line, polynomial with degrees 2, 3, 4, 5. And the polynomials that if you go and look at the squared error in the training set for each fit, as you increase the degree of the polynomials, you fit better and better. The prediction perspective on this is it will be worse if you actually look at their performance and test it. So this means that you can use cross-validation, reading out each point in turn, fitting the model on all the points but one, testing on the model that's left, on the point that's left out. And you plot the error for the different degrees in the x-axis. On the training set, you always do that, but on the test set, cross-validation, you past the real degree of the point. So this can be used not just to see how well you do when you sample, but also to try to get an estimate of how complex the model should be. And if it's now a data set where the true relationship is something like this curve, pedigree models are similar, but it was more complicated. A line would be too simple. If you were to do the same idea here, you'd see that if you start with a line, degree 1 in this plot, you actually have a very high error. Degree 2, it goes down. And then after degree 2, the test set error starts climbing back. So indicating that that's really the likely complexity of the polynomial that fits the data. So to cap this, pretty much every machine learning talk has, tutorial talk has this quote. The point is, yes, all the models are wrong. Some are useful, and they're useful in terms of being able to fit the data reasonably or make predictions that are as good as you can make them. And thinking about things from the perspective of fitting models to training data and testing them in the test sets helps you tackle all of these issues. So you might be asking now what this happens to the brains, which is the next part of the talk. But before I launch into that, questions. Which it's also the inherent have composed. Let's see.
Okay, is this better for the people online?
Yes, yeah.
Okay, so if this is good, let's just go with that. Sorry, Al. Fernando. I don't know what this got out of the talk. Yeah.
I have a question, but if it's change the direction of your plans, you can answer it at the end or whenever. But it's true that consolidation will address overfitting. But if there are any changes in the alignment of the grid of the data points associated with each of your conditions, you're gonna choose simpler model via cross-validation. Similarly, data complexity is needed for fitting a complex model. So there's a sort of bias towards preferring simpler models. I don't know if that's something that might be important to consider at this point or at some other point.
Later when we get to the issues, but yes, it's possibly the case. But yeah, all of these things will give you slightly conservative answers, but I don't think that's a problem intrinsically. But let's leave that for the pitfalls, because there's some terminology to also to introduce. So I wanted to make sure that I gave you something really concrete. So this is actually a pretty old study where people were just reading concrete nouns belonging to one of two categories, tools or buildings. They would see a word, think about it and its properties, visualize the item being named, and then there would be a blank for a few seconds. And I was also working on this. So we would take average images around the response peak to the stimulus in each trial. And I want to use this to introduce terminology because it will be easier to talk about the rest. So if you take the average image during a particular trial, it's either tools or buildings. So this would be called an example. The values on the voxels will be features, and the values they take are just the values of the activations in the respective voxels. And tools just be the class label. Again, this is just terminology that's typically used for this example. And in this case, we split for the sake of this example, we split the data into two parts for training and testing. Training is just all the examples in the odd runs. Testing is just all the examples in the even runs. Yeah. And so if we take the labels that we have in the data, we will be training a classifier on one half of the data to predict those labels, tools or buildings for each image. And then we will apply it to the test data to predict what the labels are and compare them with what the labels actually were. And out of this, you get some sort of accuracy estimate, in this case 82%. That just shows, in general, how likely are you to be able to predict on a new image which of the two things it is. And generally, people don't do prediction for the sake of doing prediction, which is the other part. So I toyed with having another slide about what question do you really want to answer, because that's often a problem that people come to us and say, I want to do this prediction. And generally, that's never the first question should not be that. It should be, why do you need a prediction? Most of the time, the reason people want to see a prediction is to say there is information about the specific label that we want to predict in the data that we're feeding in as input. And the model that does the prediction helps us understand how that information is structured. So in this case, and to get to that, let's just see a little bit about what's inside a typical classifier. The simplest one that could be doing this, and imagine you just had an image with two voxels, 1 and 2, so that I can plot in 2D, and there's only 6 examples. So each example has values of, for voxel 1 and voxel 2, those are the X and Y coordinates in this axis. And if you get a new image and you have to label it, simplest way would just be to say it is the label of whatever it's most similar to in that voxel space. The name of this is a nearest neighbor classifier. It's actually a type very used in a number of situations where you have a good measure of similarity between items. And you can use more than one point. This is just saying what's closest to it. You can, more often, fit something like a linear model that distinguishes between, that puts a line separating two regions, which would be for tools or for buildings. And if you were to fit this, generally, the problem that people face next is which one to fit, because there are many different kinds of methods that would work here: linear discriminant analysis, logistic regression, linear SVMs, etc. And again, often the question of which one to pick depends on which assumptions you can make about the data, or you can use, or if they're very different, you could use cross-validation within the training set to decide which one is better. But for the sake of this, I'm just going to show you a very simple example of a linear SVM, where the way this operates is it will take the values of each of the voxels. So I'm just mapping the values of the voxels to the voxels in the brain, and it will learn to put a weight on each one and plus an intercept, and just take the weighted combination of the values of all the voxels. And if that's greater than 0, it will predict tools. If it's less than 0, it will predict buildings. So that just gives you the two regions and the space that I was showing you in the image. And in this case, for a support vector machine, the weights of the classifier on each voxel would look like this image at the bottom. These are just 8 different slices. And if you see negative weights, those weights are pulling the decision towards saying it's a building. And it's not surprising in this case that they are kind of around the parahippocampal gyrus. And conversely, if the weights are pulling towards tools, they are going to be higher around the motor sulcus. It's in central sulcus, so motor cortex. And this is really it for fitting a linear model and hoping it will tell you where the information is coming from. If you have more classes, the interpretation is a little bit more complicated. So, but this is usually why people fit a model like this. You could also fit models which are more complicated. This is also something that people often ask me, why not something more intricate? So for instance, if you're using something like a quadratic SVM, it can learn to predict based on what voxels are doing, but also what the interactions of voxels are doing. For something like tools and buildings, I don't think the interactions of voxels matter very much. In other problems, they might matter to some degree. Or people often ask me, why not train a neural network? Because that's just something that's capable of learning from the voxels, many different combinations, which are interesting patterns of co-activation between the voxels. Usually the problem with that is that you never have enough data in most situations people encounter to learn a really fancy neural network. But the one caveat to all of these things is that the more complicated the model gets, the harder it is to understand what exactly in the data has information about the label and how is it connected. Though, just to say it's complicated, it's not to say it's impossible. I put a pointer there to a paper we wrote comparing a variety of methods to look at interpretability in neural networks, because it's most likely what people would be trying these days. But all this to say, there are many kinds of models, and deep down, most of them still turn into something linear. It's just that it might be something linear on complicated combinations of features learned from the original features. But also to say, most of the time, the classifier for the sample sizes people have, the models people can fit are relatively simple, so this doesn't matter too much. The other part that I glossed over and I wanted to cover because it's important is if you are testing a classification result, this is similar for the regression, just a little bit more complicated, so I'll just stick to this for now. You would have true labels for each example. You also have the predicted labels, and you can see that in some cases you got it right, so it's in white. In other cases, the true label is different from the predicted label that's marked in red, and it's an error. The accuracy is just how many of these are correct out of the test set. And the null hypothesis you have is that the classifier learned nothing at all and is predicting completely at chance. So under that setting, if you're using the null hypothesis framework, what you need is a distribution of what the accuracy would look like if the null hypothesis is true. And in this particular case, it's the analytical distribution for a chance level is just a binomial distribution with as many draws as the number of test samples. And given that the p-value is just how unlikely is the accuracy that you got, or the number of examples correct, given that the null is true. And the reason I'm belaboring this is that on the right, I'm showing you what does this distribution look like, the null distribution, if there's only 10 examples, n equals 10. It's pretty wide. It could go all the way from 0 to all the way to 1. So by chance, you could easily get a high number in the accuracy. And it's still pretty wide for n equals 20. It's starting to narrow for n equals 50. At an n equals 100, it will be pretty centered around 0.5 and pretty tight. The line in red is the cutoff for a 0.05 p-value. So all this to say, the accuracies you get are an estimate. If you have very few examples, you are pretty uncertain about what the actual accuracy is. And you also need to take into account, if you do this for multiple models in one paper, that you need to correct for multiple comparisons. So if people get a high accuracy, they will say, this is good, right? No, depends on how many examples you actually have and how many tests you're making in a single paper. Does this make sense? And needless to say, we're always available to talk to people about testing the results that they have. And we can know of many different ways we could do it beyond this. And we can figure out how to test almost anything if we have to. This is just for one specific instance classification. So the second thing that I wanted to talk about in terms of making a classifier work in real data is classifier answers the question, is there information about my label in the data? But sometimes it needs help to do that. For two reasons. One is you might want to restrict how many features you actually have going into the classifier because it will perform better, or to make it easier to interpret the fact that it can pick up information. For instance, maybe the question should be, is there information about the thing I care about predicting in this particular region of interest? Or is there information at this point in a trial versus that point in a trial? Or is there information in a particular condition, but not in another one? So these are all things that people have done, and I could spend the whole afternoon summarizing papers that restrict it in voxels or other things in a particular way. But all this to say, the general name for this type of restriction is called feature selection, and it literally means you are removing certain features from consideration, just regions of the brain or anything else. In this case, it has to be regions of the brain. And then you restrict them from consideration, you train a classifier, and you restrict them also in the test set, and then you can deploy it. It's also possible to do more clever restrictions, like restricting by the experiment phase. So I have friends who were interested in recall experiments, and they would train classifiers on people learning items of a particular semantic category, and they would learn to distinguish from the study phase. And then they would deploy the classifiers while the people were doing free recall, so that you could try to use them just as sensors for a particular mental state. That's a very cool use. But you could also train models based on trials where people were successful versus not, where they got a reward versus not. I'm mentioning all of these not, again, because these would take a whole afternoon to review. More to say, you can think of doing prediction and get a lot more leverage out of the models by having an a priori hypothesis for what exactly you want to ask that question about. In terms of other modalities beyond fMRI, I've worked with people doing fitting prediction models, classification or regression for structural data. And so in this case, generally for structural, people are grouping voxels into a brain region and maybe transforming into a mesh and maybe making a predictor from that, or deriving other measures, which I'll talk about in a second. For diffusion, people will do some measure that counts how many tracks pass through a region, and there's a variety of them, and they can derive some form of structural connectivity matrix. For resting state fMRI, they would derive a functional connectivity matrix. But the point really is what sort of features come out of these transformations of the data. For structural data, it could be at every point in the vertex in the brain, or for a given region of interest, you'd be looking at gray matter volume, at cortical thickness, at surface area, or how these measures could vary between regions. I've seen all of these. For structural or functional connectivity, you could just use them directly, and your model takes into account connectivity between every pair of voxels or every pair of regions, or between different networks. People aggregate in all those ways. Or you could transform the connectivity matrix into a graph, and that lets you derive graph theory measures. These may or may not be applicable to your problem. Most of the time I encounter graph theoretical measures as people are just trying measures and see if one of them correlates with their target, which is not super principled, but that's just something I encounter often. So all this to say, this framework works for measures derived in all these ways. It's not restricted just to functional MRI by itself. And also not restricted to doing classification problems in psychology. So most of the problems we encounter are actually patients versus controls. Is there any difference between them? Can we predict whether they will respond to a treatment, or what the disease outcome is going to be? Or it could be how intense are symptoms in some rating? What's the time for symptoms to appear? For instance, transitioning from MCI to dementia, or various patient characteristics. So these are all things that can be solved using machine learning. And in general, feature selection does tend to be one of the things I listed, but in the absolute worst case, you could always, if you're say trying to distinguish between, you're trying to predict a problem that's regression rather than classification, you can do correlation tests on individual matrix entries to decide which ones to pick or anything like that. So it doesn't need to be a selection that's purely driven by scientific criteria. It can just be about raw, does this variable contain information about my target? And these are already the things that I talked about. So I kind of wanted to, so let me just jump to this because I wasn't sure if we were going to have enough time. I wanted to end by going over potential issues that I see. I illustrated this with the circles of hell from Dante because it gets progressively worse as we go. So start with this with the less bad ones. If people are working with small sample sizes, it's quite possible, as I was showing you before, that you'd get high values of classification accuracy or R squared if you're doing regression purely by chance. And so you kind of have to do a power analysis ahead of time to say, what's the biggest effect size that I could find? And is this sample large enough to detect it? Because if it's not, then odds are you just got it by chance. It's not a bad idea to do a power analysis anyway, because it makes people think about which analysis they're actually going to want to do. I mean, I know this sounds silly, but I've had people tell me, it's great that we did this. I really thought about it. We're not thinking about it before, but this happens. I'm glad if people ask, and we're always delighted if people say we want to do a power analysis, because then we have a chance to talk about what is the effect of trying to find. Is this analysis suitable? Is something better? So I encourage people to do that. The other part is, or kind of the converse from this is, let's say that you are pretty sure you did everything right, and you detected a really small effect. So in this case, it would be chance is 50%, you got 60%, but your sample size is large enough that this is still significant. Question one is this useful at all? Maybe for something, for a diagnostic, 60 versus 50% accuracy is not useful. If you were 60% accurate at predicting market movements and you were in a hedge fund, they would be delighted and they would make a lot of money from it. So it really depends on what you're trying to do with the number. But generally, when you see a number like this, what's usually more interesting is to see, do you always get 60% across all the parts of the experiment? Or is it really that some of the time you're predicting really well and another part you're not? Maybe the subject started moving more towards the end. Or maybe there are trials where you can predict and trials where something else is going on. So often looking at where the errors are and whether they're correlated with anything might be pretty revealing when you have a low accuracy like this. And the third one is, if you have some sort of class imbalance and one model, one of the classes is more frequent than the other, then the null model I was describing for the binomial is no longer valid. So often people would come to me and say, I got 90% accuracy, but most of your examples are negative. At distinguishing patients from controls, but 90% are controls. Maybe your classifier is just deciding that everyone is a control, and you do quite well just because of that. So there are a variety of techniques to address this. It could be that you either undersample the class that's more frequent, you oversample the more frequent one, you generate synthetic examples, and there's also ways of doing non-parametric nulls that respect these ratios. But this is a situation where definitely you should talk with our team. So these are all things that, at worst, they will give you somewhat bad results, but I don't think they will necessarily lead you astray very far. The things that do lead people astray would be, first, p-hacking, which is you try many, many things, usually doing a cross-validation in a data set that you have, and you only report one. Bad news, that could just be something that, even though it's out of a cross-validation where you're getting some estimate of how well you do on data that model was not seen on, as we were seeing earlier, you're still going to have an optimistic bias because you tried it many times and you're picking the one that looks best. The best way to guard against this is do all your model development on one sample, maybe using cross-validation, decide on what you want to do, and then you test it on a sample you've never seen before. If you want to be really, really thorough and impress your reviewers, consider doing a pre-registration before you do this. You're literally saying, I did all this development, I'm going to commit to this model, and this is the one I'm going to test on a separate data set. Unfortunately, a lot of results in the literature are the result of p-hacking. And I know because the sample sizes are too small for them to have an effect as big as they have. Or I know because there's a suspicious combination of lots of little decisions that, yes, if you just go just so and just so and just so, you get this nice result. But if you do anything else, you don't. Because I've reanalyzed the same data sets, and I know that across the board, occasionally you get something that looks good by chance, but otherwise everything does not look better than that. So all this to say, if you look at older papers that train any sort of classifier, be careful and pay a lot of attention to how they got to the result that they got to. And consider that they may be p-hacked because people just didn't know any better. The second thing that also comes up is called circularity or double dipping, which means you have a test set, but you use the training and test set together to make decisions because it's kind of cheaper. For instance, you're going to do a cross-validation, but you don't want to run your feature selection as many times as you have faults. And you just use all the data together to select features, and then you run the cross-validation. You're going to get a really inflated result because of that, and a result where there's none at all, most likely. So the best way to make sure that this doesn't happen, well, one is thinking carefully through it, but the other one is you get a result, any result on any experiment, you just try the following. You have your whole analysis pipeline, permute the labels that you have for the examples, and then run your entire pipeline to get a result. If you have a mistake like this in your code, then you'll still get a result that's better than chance, even though you permuted all the labels. It's a really good sanity check to make. It's very cheap. And this has caught issues with my results a number of times. I mean, I've been around long enough that if I see a good result, I assume it's wrong. It's kind of sad, but it's often true. But this is a good sanity check that will save you a lot of trouble. And as a reviewer, if things look too good, I often ask for this. And maybe a third of the time, it turns out that they did something like this. And it's not necessarily obvious. It might just be something subtle that introduces bias because you are somehow kind of compensating for something in the test set. It's hard to pick up on, which is why that sanity check is maybe the easiest way of seeing if that's happening. And finally, and these days you don't see this anymore, but you did maybe 20 years ago, is people just report results of training and testing the models on the same data. And you get vastly optimistic bias in this, which is again why in old papers, if you see really high accuracy claims, you should go back and see how big is the sample size, were they careful with how they separated test sets, did they also not look at the test data when selecting features or something like that. But this doesn't happen too much. I think people have learned about the methods in the last 20 years, so they typically don't do this, but in old papers, it's happened. So all this to say, what I wanted you to take from this was really whether to use machine learning or not depends on whether prediction matters to you in some sense, and specifically whether getting generalization of a certain prediction result is important to you. If that's helpful, it makes sense to use machine learning techniques. Otherwise, it might, to answer the other questions, it might make sense to use something else. And we are always happy to talk to people about what might be most adequate, because our team has mathematicians, machine learning folks, but also statisticians, and we know about techniques to answer all of these questions and more. So thank you for listening to me about all of this, and we're always happy to talk.